What up, y'all? Mr. K here. I'm going to try to teach P6, rational expressions. I don't know what's going on in terms of teaching, but I just wanted to provide you with these notes in case it would be helpful. So let's get started. So I'm just going to go through all of these as well as all of the examples, and then it might be a couple days worth of notes here. So we got evaluate the following. 1/2 times 1/3. With multiplication, we multiply straight across and we have fractions. So 1 times 1 is going to give us 1, and then 2 times 3 is going to give us 6. How's that showing up on the screen there? I'm going to use a little darker color here. Maybe that'll help. But also, I might screw it up because it's a pen. So I know I told you not to use pen, but here it is. All right, we got 1 divided by 1, excuse me, 1/2 divided by 1/3. Now with this one, we have to reciprocate the second fraction. Reciprocate means flip over, so and then this is also going to change into a multiplication. So that's going to become 1/2 times, and then we flip this over, so it just becomes 3/1. And then now we multiply the same way we did over here. So we do 1 times 3, and that's going to give us 3, and 2 times 1 is going to give us 2. So our final answer for that would be 3/2. Let's box our answers. All right, now we have 1/2 plus 1/3. Now the problem with this is that when we add or subtract, we have to have a common denominator. Common denominator means the same thing on the bottom here, so we got to figure that out. Well, an easy way to do that would be multiply both denominators together, which we'll do later on in this lesson also. So 2 times 3 is going to give us 6. That's going to give us our common denominator. So what we have to do then is we have to take 1/2 and turn that into sixths. You might know exactly what that looks like in terms of sixth grade. If you're not sure, well, we multiply that by 3/3, which is a fancy 1, right? 3/3 is just 1, but it's written as 3/3. And then we add to that 1/3 times 2/2, because we have to multiply this by 2, and we have to multiply the whole fraction by 1. So now we get 3/6, which is these two things together, plus 1/3 times 2/2 is 2/6. Then we just add straight across, only the tops, right? We have 3/6 plus 2/6, and that's going to give us 5/6 in total, right? If we had a circle that was split up into sixths, and 3 of those were shaded here, and then we added 2 more sixths, 1, 2, we would have 1, 2, 3, 4, 5 in total shaded. So that's why we get 5/6. These don't get added together. Don't make that mistake of saying 5/12, right? 6 plus 6, we don't add the denominators. Terrible mistake. Please don't do that. Same thing with subtraction, except once we get to this point, we have to subtract them. So 1/2 minus 1/3, we already did the common denominator, so let's just go down to here. So we have 3/6 plus 2/6. Whoops, that's not plus. See, there's my pen. Minus, that becomes that. So 3/6 minus 2/6, that's just going to equal 1/6. And that's our final answer for that one. Okay? So just a reminder about how to combine those fractions together. All right, I'm going to slide down here. So now what we're going to start off with is rational expressions. I'm going to read some of this to you and point out the important stuff here. A rational expression is the quotient, right, divided by two things divided by each other of two polynomials. Some examples are, we got this here, x minus 2/4. Another example is 4/x minus 2. We got x over x squared minus 1, and x squared plus 1 over x squared plus 2x minus 3. Okay? Polynomials, terms that are together. We got two terms here. This is a binomial over a trinomial. We got a monomial over a binomial, monomial over binomial, and then a binomial divided by a monomial. All right, so all of these classify as rational expressions. All right, the set of real numbers for which an algebraic expression is defined is the domain of the expression. Now remember, domain means when the expression is possible. And the main thing that we're paying attention to with our domain is that the denominator can never be 0. That's the big thing that we want to focus on, right? So that we're going to make the denominator 0. So we must exclude numbers from rational expressions domain that make the denominator 0. And we'll talk a little bit about how to do that right here in this example. So the first one that we have is 4 over x minus 2. So find all the numbers that must be excluded from the domain of each rational expression. Well, 4 over x minus 2, this is what we're concerned with in this example, the denominator and the denominator. In all three of those examples, we're going to focus just on the denominator. So the way I like to write it is x minus 2 cannot equal, right? That symbol means cannot equal 0 or does not equal. Then I just solve that. So I add 2 to both sides. Then x cannot equal 2. And that is the domain for example A. Basically, any number besides 2 works for this example. Let's look at this one here. So now x squared minus 1. X squared minus 1 is our denominator, and that cannot equal 0. Well, I got to solve for x in this situation, and hopefully you're noticing that x squared minus 1 is a difference of perfect squares. So that means we have x plus 1 and x minus 1, right? The square root of x squared and the square root of 1, and then we put it into this pattern. And those two factors cannot equal 0. Now we use our zero product property, and we have x plus 1 cannot equal 0, and x minus 1 cannot equal 0. Subtract 1, x cannot equal negative 1. Am I still on the page here? Yep. And add 1 to both sides, and then x cannot equal 1, positive 1. So x cannot equal negative 1, or x cannot equal positive 1 in order for this to be a rational expression without the denominator of 0. So this is the domain of example B. Now let's look at C. So we got x squared plus 3x minus 18 cannot equal 0. Yeah? All right, now how do I solve this one? Well, I got to factor it. What are my factors of negative 18 that add up to a positive 3? So as I talked about last week, we're just going to start to move towards this right now in this first one. So we got x squared. That's going to make x and x. And then factors of negative 18 that add up to positive 3. That's going to be a positive 6 and a negative 3, because 6 times negative 3 gives us negative 18, and 6 minus 3 gives us a positive 3. So now we have our two terms. We're kind of at this point right here that we were over in the previous problem. So now we set up our zero product property. X plus 6 cannot equal 0, and x minus 3 cannot equal 0. Subtract 6 from both sides. X cannot equal negative 6, or add 3. X cannot equal 3. All right, so that's how we exclude numbers from the domain. The domain can be everything except these two numbers, this one number for each of these examples. All right, let's flip on over. All right, let's get that centered. There we go. A rational expression is simplified. So simplified that's the big word that we're focusing on right now, because you'll see that like in the instructions, it'll say simplify the rational expression. Simplify right there. That's what we're going to focus on. If its numerator and denominator have no common factors other than 1 or negative 1. The following procedure can be used to simplify rational expressions. This is really helpful, okay? And I'll show you a couple examples of what that looks like. First, you're going to factor the numerator and the denominator completely. Second, you're going to divide both the numerator and the denominator by any common factors. Divide, another way to think about this that I've talked about it so far this year, is canceling out things that are exactly the same. I'll show you what that looks like right now. All right, so we got the numerator and the denominator. We got to factor that. Well, the denominator is already factored. We can't do anything with x plus 1. So let's go ahead and keep x plus 1 there. But I do know that these two have a common factor of x squared. So I'm going to factor out that x squared. That's going to leave me with x plus and 1 right there. So now I have everything, my numerator and my denominator, completely factored. And now it says divide both the numerator and denominator by any common factors. So now in this case, what I have to look at, remember, factors means things that are multiplied together. Right? And in this case, x squared and x plus 1 are multiplied together. X plus 1 is also, that's the only factor on the bottom here. So what's common? Well, x plus 1. And what happens in this situation is they both get divided out and they both reduce to 1. Just like if you had, in another example, 2 over 2, right? Those would both reduce, and that would equal 1. Well, in this case, they both reduce to 1. So they kind of go away in that we don't see them anymore, because really what this turns into is just x squared times 1, which are these two things here, or we just write it as x squared. But we can't forget what we did before with the domain exclusions. So we also have to take a look at our domain when everything is factored and make sure that we remember to exclude the possible domain. So in this situation, we have x plus 1 cannot equal 0. Subtract 1 from both sides, and x cannot equal negative 1. So our final answer for a simplified version of example A is that we have x squared as a simplified version, and we also have to include this restriction that says x cannot equal negative 1, because otherwise this would be equal to 0, and then the whole thing falls apart. All right, let's take a look at example B. I'm going to kind of work over this way to get out of the way of this stuff here. So I factor the top and I factor the bottom. See if you can do that. You're welcome to pause the video and try that out on your own, but I'm going to go ahead and do it right now. So I look up top and I have a trinomial, and I need to factor that into two binomials. Factors of 5 that add up to 6. Well, that's going to be x and x because of my x squared, and that's going to be plus 5 and plus 1. Yeah? 5 times 1 is 5, and 5 plus 1 is 6. Now, x squared minus 25. This is like the example we saw on the previous page where you have x squared minus 25. X squared is a perfect square, 25 is a perfect square. I take the square root of both of those, and I put them in that pattern where I do x minus 5 and x plus 5. Right? The difference of perfect squares right here goes into this pattern where you take the square root of both of them and add 1 and subtract the other. Now I'm at number 2, divide both by the numerator and denominator by any common factors. This binomial is multiplied by this binomial is multiplied by this binomial. Therefore, they're multiplied together, they're all factors. So now I reduce x plus 5 and x plus 5. They're both the same, therefore they're going to reduce to 1. So now what I have is I've got these two terms, and I have x plus 1 over x minus 5, right? And they're not the same, so I can't reduce anymore. And I also have to check my domain because I have these two terms right here. Now, why didn't I do the domain right away and set x squared minus 25 equal to 0? I could have. I very well could have. But if I'm going to do all this work of factoring, I'm just going to wait and do it that way as well, because I have to factor it to get to this step of the problem. Now I can just set these two terms equal or not equal to 0. X minus 5 cannot equal 0, and x plus 5 cannot equal 0. And in this case, x cannot equal negative 5 or positive 5 when I solve both of those. So this is my domain restriction, and this is my simplified version. And both of those are necessary in order to give an answer for a simplified version of this rational expression. All right, let's keep going here. So now what we have is we've got multiplying rational expressions. Now, what I want you to notice here is that 1 and 2 are exactly the same as 1 and 2 up above, right? So we've got our two examples here, 1 and 2, about how to simplify. You read these words, they're exactly the same as what we have down here. So basically, the first two steps of multiplying rational expressions are to simplify the rational expression, which makes sense because when you simplify it, it's going to be a lot easier to multiply things together. So let's go ahead and take a look at what that looks like. And then number 3 says multiply the remaining factors in the numerators and multiply the remaining factors in denominators. Just like we did with 1/2 times 1/3, we multiply straight across. So let's take a look. First step, factor all numerators and denominators completely. Well, x minus 7 and x minus 1 are totally factored, so we can just rewrite those. X minus 7 over x minus 1 times. Now, x squared minus 1, again, that's the difference of perfect squared, just like we saw up above with x squared minus 25. So that's going to be x minus 1 and x plus 1 over 3x minus 21. Well, the common factor here, there's no squared, so I can't do any of this nonsense. But then 3x minus 21, they have a common factor of 3. They don't have any x's over here, so all I can factor out is going to be a 3, and then I'm left with x minus 7. All right, cool. Now I can multiply across, and that's going to give me x minus 7 times x minus 1 times x plus 1. And then over here on the bottom, I'm also going to have all three of these factors, right? I got 1, 2, and 3 factors. So I have 3 times x minus 1 times x minus 7. All right, so now I did the first two. I factored all numerators and denominators, and then I divided the numerators and the denominators by common factors. Now I have to I multiplied across. Then I'm going to cancel out. I'm going to simplify what's the same on the top and the bottom. I don't do it here, right? I don't cancel things out here. I multiply straight across, this times this and this times this, and then I get one big expression here, and then I simplify. So I have an x minus 1 on top, I have an x minus 1 on the bottom, and I have an x minus 7 on the bottom and on the top as well. So all of those are going to reduce down to 1, which means that now all I'm left with is x plus 1 over 3. Now that's my simplified version of the multiplied rational expressions, and I still have to look at my denominator to make sure that I do my domain exclusions. Now 3 can never equal 0, so I'm not worried about that, but I have x minus 1 and x minus 7. So x minus 1 cannot equal 0, and x minus 7 cannot equal 0 also. So add 1, x cannot equal 1, or add 7, x cannot equal 7. So again, both of these are necessary to give a complete answer when we're multiplying rational expressions. All right, we're getting there. Okay, dividing rational expressions. Now this is a little bit different, but it's also pretty similar because when we divide, we're going to take this, turn it into a multiplication, and flip this. The word I mentioned earlier was reciprocate. Oh, I'm not centered here. Reciprocate the fraction over here on the side. Okay, so let's go ahead and rewrite it. So now we have x squared minus 2x minus 8 divided by x squared minus 9 times x plus 3 over x minus 4. Now, some of you might be sitting there thinking, well, why didn't you factor this stuff right away? I didn't want to do too many things all at once. I tend to get confused and make mistakes if I try to do too many steps at once. So as I'm sure you'll see me do, all I'm doing is I'm turning this to multiplication and I'm reciprocating the second term. So now what I'm going to do is I'm going to start to factor my my numerator and denominator. Well, this is fine, so I don't have to factor any of that, but I can factor both of these. So let's go ahead and rewrite. So now I have x squared minus 2x minus 8. Factors of negative 8 that add up to negative 2. Well, that's going to be 4 and 2. So now I have x times x, because I got x squared. And then I'm going to a negative 2, so that's going to give me a negative 4 and a positive 2. Right? Negative 4 times positive 2 is a negative 8, and negative 4 plus 2 is a negative 2. Great. Now I have to factor the bottom. Difference of perfect squares. X squared and 9 are both perfect squares. So now I have x plus 3 times x minus 3. Those are my two factors. And then I still have this other thing that I have to multiply in here. I'm going to write it, squeeze it in here. X plus 3 over x minus 4. All right, so now everything is factored, and I can now multiply straight across. So I'm going to rewrite all of this multiplied straight across down here. So we got x minus 4 times x plus 2 times x plus 3 divided by x plus 3, x minus 3, and x minus 4. All right, now I'm at the last step where I have to look top and bottom to see what's identical. So my x plus 3 is going to reduce to 1, and my x minus 4 top and bottom are going to reduce to 1. Now I'm left with x plus 2 over x minus 3. So that is my simplified rational expression after dividing, and I still have to do my domain restrictions. So x plus 3 cannot equal 0, x minus 3 cannot equal 0, and x minus 4 cannot equal 0. Therefore, x cannot equal negative 3, positive 3, or 4. And both of those are necessary. Okay? All right. Let's keep going here. Like I said, I'm going to teach the whole lesson. This might be several days worth of work in terms of lessons and mini lessons and whatnot, but I just want to get this video out there. All right, subtracting rational expressions with the same denominator. So 5x plus 1 over x squared minus 9 minus 4x minus 2 over x squared minus 9. Now, like I said earlier when we did the example before, when we subtracted, we have to have the same denominator, 6's. Here we have the same denominator, so we can subtract what's in the numerator from each other. So what this is going to equal is 5x plus 1 minus, and I got to put this whole thing in parentheses because we're subtracting this whole term here, 4x minus 2 divided by x squared minus 9. All right, so what this is going to equal, now this negative sign is going to get distributed in there and change the negative signs of both of those. So 5x plus 1 minus 4x plus 2 divided by x squared minus 9. Now, I'm not going to factor this yet because I don't know what's going to happen up top. I might need to factor this to be able to reduce, but I'm not sure what's going to happen yet, so I'm not going to bother messing with that. I see it's a difference of perfect squares, and I know where it's going to go, but let's see what happens. So this is going to equal 5x minus 4x just gives me x, and then plus 1 and plus 2 gives me plus 3 over x squared minus 9. Now, x plus 3 is going to be one of these factors because I know this is going to be x plus 3 and x minus 3. So now I'm going to go ahead and factor that since it will simplify. So I got x plus 3 over x minus 3 times x plus 3 because of our rule of the difference of perfect squares. Now, let's go ahead and do our domain restrictions because we know we're going to have that. X minus 3 cannot equal 0, and x plus 3 cannot equal 0. Okay? Therefore, x cannot equal 3 or negative 3. So those are our domain restrictions. Now we simplify our expression here by dividing top and bottom, x plus 3 and x plus 3. Now that's going to equal, now pay attention to this one. Remember I said x plus 3 over x plus 3 was just 1. So therefore we have our 1 up top over x minus 3. And that's our final one. Sometimes you might be tempted to just leave that blank and just write your answer as x minus 3, but we have our placeholder of that 1 on top because this did divide out. So we've got to put that 1 up top. Okay, so we got our simplified expression and we have our domain restrictions. Now is when it gets a little bit more complicated. So here we are at example 6, subtracting rational expressions having no common factors in their denominators. Now in this situation, what we're going to have to do is we're going to have to make a common denominator. And the easiest way to make a common denominator is by multiplying the denominators together, just like I did in the warm-up, right? Here we had the denominators multiplied together, the 3 and the 2 and the 3 and the 2 were multiplied together. With algebra, we can do the exact same thing by multiplying the denominators together. And what we need to do is we need to multiply by that fancy 1. Remember how I said we're multiplying here by 3 over 3 and by here as 2 over 2? Well, I'm going to do the same thing, but just with my algebraic expressions. So here, what I'm going to do is I have 2x minus 3 and x plus 3. I have to multiply those two things together. So in my first term, I've got x plus 2 over 2x minus 3. And I have to multiply that by a fancy 1 where x plus 3 is my fancy 1. X plus 3 over x plus 3. See how that's the same thing top and bottom? So that's really just a 1. And then we're going to subtract 4 over x plus 3, which is my term right here. And then I have to multiply it by my fancy 1 with this as my term. So that's going to be multiplied by 2x minus 3 over 2x minus 3. So this is my original problem, and these are the terms here that I used as my fancy ones to find my common denominator. All right, let's go ahead and multiply that out. This gets multiplied by that, and this gets multiplied by that, and this get multiplied together. So now for our first term, we have x plus 2 times x plus 3 over 2x minus 3 times x plus 3 minus 4 times 2x minus 3 over 2x minus 3 times x plus 3. Okay, so here we go. Now this minus sign is going to affect all of this, and then we've got these here. Now, I'm not going to mess with my denominators just yet. I don't know if there's anything that I really need to do with them in terms of foiling them out or whatnot. I don't really want to mess with that if I don't have to. So I'm going to just leave that be for the time being and see kind of what happens as the problem moves forward. Okay, So let's go ahead and mess with this stuff up top. So x plus 2 times x plus 3, when I FOIL that out, I'm going to get x squared, and then 2x and 3x, so plus 5x, and then 2 times 3 is going to give me a plus 6x. Oops, sorry, just 6. Divided by my denominator here, 2x minus 3 times x plus 3. Now we're getting into some algebra. Now I'm going to distribute this. I've got minus 8x and then, so this is a 4. I'm multiplying this into here and there. So it's going to be minus 8x minus 12. Lost track of my sign there. Divided by 2x minus 3 times x plus 3. Now, some of you might be looking and saying like, well, Mr. Kowalczyk, why didn't this become a negative 8x and not a positive 12? It will, but I'm going to do that once I put all of these under the same fraction. Right now, there are two different terms that are added and subtracted to each other, so I don't want to mess with that just yet. I'm just going to, like I said, I don't like to do too many things at once because I make mistakes. So now let's let's combine and subtract all of this stuff together. But watch what I do. So first off, I've got x squared plus 5x plus 6. Now I have a minus 8x minus 12 in parentheses, divided by 2x minus 3 times x minus 3. So now I have one whole fraction with the subtraction happening up top, and I've got that all ready to subtract. Now I'm going to distribute this negative sign into here and here, and I get x squared plus 5x plus 6 minus 8x, and then negative times negative becomes a positive 12, divided by 2x minus 3 and x minus 3. All right, cool. Now I can combine my like terms, and I get x squared, positive 5 and negative 8 gives me a negative 3x, and then plus 6 and plus 12 gives me a plus 18, divided by 2x minus 3 and x minus 3. Cool. Awesome. All right, so now what are my factors of positive 18 that add up to negative 3? Well, there aren't any, because 6 and 3, 6 times 3 would give me a positive 18, but that would add up to a positive 9, and that's not what we have here. Negative 6 and negative 3 would multiply to give me a positive 18, but add up to give me a negative 9. Therefore, the numerator is prime, which means we can't factor it. So we're done. We can't reduce this anymore, with the exception of still having to find our domain restrictions. Yeah? Okay, so let's go ahead and find our domain restrictions. 2x minus 3 cannot equal 0, and x minus 3 cannot equal 0. Add 3 to both sides. X cannot equal 3. Add 3 to both sides. 2x cannot equal 3, or x cannot equal 3 halves. So now we have our domain restrictions and our simplified fraction, and we're all done. Okay? Yay. All right, last one, and then this video will be over. Now we're adding rational expressions with different denominators. Same exact process, except we don't have this negative sign here and here, which is going to distribute in there and change everything else. Okay? So now, obviously, you're looking at this one and you're saying, this is a little bit more complicated. It's not exactly the same process, Mr. Kowalczyk. You're right. We've got a trinomial down here, and we have a difference of perfect squares right there. So let's go ahead and start out by factoring these to simplify them, and then it'll be easier to find our common denominator. All right, so x plus 3 on top over x squared plus x minus 2. That's going to factor out into x minus 1 and x plus 2, right? We want to multiply to get to negative 2 and add to get to negative 1. So that's going to give us these two. And then we have plus 2 over x plus 1, x minus 1. All right, so now we've got both of these here. And what we want to do is we want to look at, we need to have all identical terms in each of the denominators. So here we have an x minus 1 and an x plus 2, and here we have an x minus 1 and an x plus 1. So now what's missing from this side is x plus 1. And what's missing from this side is x plus 2. So I have to multiply those. Those are going to be my fancy ones in each of these situations. So now what I'm going to do is I'm going to rewrite it as x plus 3 over x minus 1 times x plus 2. Now I have to multiply by my fancy 1 of x plus 1, because that's what's missing in my denominator, times x over x plus 1, right? And then I add that to 2 over x plus 1 times x minus 1. And my fancy 1 in this case is going to be x plus 2 over x plus 2, because that's what's missing in this denominator. Now, if you look at my denominators, I have x minus 1, x plus 2, and x plus 1, and x plus 1 times x minus 1, and x plus 2. So I've got all three terms in my denominator. Therefore, I now have a common denominator, and I can multiply across. All right, coming down here, x plus 3 times x plus 1, my first term, over all three things, x plus 1, x minus 1, and x plus 2. And I'm adding to that 2 times x plus 2 over x plus 1, x minus 1, and x plus 2. Again, Mr. Kowalczyk, why didn't you distribute the 2? I don't like to do too many steps at once because I make mistakes. All right, now let's go ahead and we'll FOIL this and we'll distribute that. So that's going to give us x squared plus 4x plus 3 over x plus 1, x minus 1, x plus 2, plus 2x plus 4 over x plus 1, x minus 1, and x plus 2. Okay. Now we can write these together as one expression. X squared plus 4x plus 3 plus 2x plus 4, everything's plus, no signs change, over, here we go again, x plus 1, x plus 2, and then x minus 1. I didn't write them in order that time. Doesn't matter, they're all multiplied together. All right, now we combine like terms. 4x and 2x gives us 6x. So we got x squared plus 6x, and then 3 plus 4 gives us plus 7 over x plus 1, x minus 1, and x plus 2. All right, now, factors of 7 that add up to 6. There are none, right? It's got to be plus, so they have to be the same sign. 7 plus 1 is going to give us 8, not 6. Negative 7 and negative 1 is going to give us negative 8 and not 6. Therefore, this is prime. So we can't factor it. So this is our simplified version of our addition. And then finally, we have to do our domain restrictions. X plus 1 cannot equal 0. X minus 1 cannot equal 0. And x plus 2 cannot equal 0. Yeah? So therefore, x cannot equal 1, negative 1, or negative 2. And we've got both our answers, domain restrictions, and our simplified fraction in order to get our answer. Okay. All right, I'm going to close out with another joke. So I heard this one. There was a dad who was telling jokes to his wife while she was in labor having a baby. And the joke he said was, why was the baby excited to be born? And the baby was excited to be born because it was getting tired of the free womb and board. Yes, the free womb and board. If that one wasn't good enough for you, I'll tell you this one. Why did the mother go to the ocean in order to have her baby? Give up? Because she wanted a C-section. All right, y'all. I hope these notes were helpful. I will probably do another video with some homework problems and some practice problems in order for you to kind of master this stuff as well. Take care, and hope to see you soon.